This is a properties of water thing. And here I am, keeping my water company. So, I've got some pepper. And I'm sprinkling that in there. Now, you know what? I should call on somebody. I want to know what is more dense, pepper or water? Actually, if somebody will blurt out an answer before I can call on anybody, then I won't call on anybody.
Water.
Water is more dense?
Yes.
Pepper is more dense. So, but that was a good try. So this is like the paper clip. The pepper will float on the water, but if I were to go knocking it around, here, let me see if I can turn this sideways. So you can see it floating there. If I stuck my finger in here and I started to push it, once I pushed it under, it would sink. So generally, pepper is more dense than water, but it floats because of surface tension, just like the paperclip floats. But there's a cool thing you can do relating to surface tension with some soap. Oops, I guess I should have. I have some, it's like Palm Olive brand soap. And it only takes a tiny bit. Here I actually have a paper clip. Luck would have it. Since I was talking about that. And I could probably just get some of this scummy soap from the edge, but just to make it there. So I don't know if you can put my hand here, maybe you can see then. Focus? Okay, there's a tiny bit of soap on there. And here, watch what happens when I touch this paper clip to the water. There we go. So a couple of things happened. One, you can see that all the pepper just pulled to the side. And then the next thing you can see is that a bunch of the pepper is sinking now. So if I get enough soap in here, this will definitely, well, I guess I shouldn't say definitely, it'll almost certainly sink this pepper. At least most of it. Put a little bit more. I'm going to just go overboard with soap now. Oh no, my soap sank. So now I'm creating soapy water, and oh, you know what? I just realized when I did that swirly thing, I never went over the solution to the little riddle that I gave you the other day relating to getting the cork to sink in the middle, or stay in the middle. I was talking about why the cork went to the sides and wouldn't stay in the middle. But I never really showed you how to make it stay in the middle, and there is a way to do it. So the swirling thing I did, it's kind of cool. It concentrated all the pepper right in the center. But now the pepper's at the bottom. Let me just give you a side view of that. So the pepper was more dense than water all the time, just like steel is more dense than water, which is what allows a paperclip to float. But soap is special. Remember, hydrophobic means one thing, hydrophilic means the other. Remember which one likes water? Which one is attracted to water? Hydrophobic or hydrophilic? I'm going to pick somebody.
Hydrophilic.
Oh, you beat me to it. Hydrophilic. Hydrophilic likes water, hydrophobic doesn't. So if I put oil in here, the oil wouldn't mix with the water. If I put, I don't know, water in there, of course the water would mix with the water. And all kinds of things are actually attracted to water, which we'll get to later. But soap is both. Soap is both hydrophilic and hydrophobic. And I was a little behind this morning, so I didn't find this. Hey, Ms. McGurk, good morning. But let me show you a soap molecule.
Morning.
Good morning. Soap molecule, I'm going to write surface tension because I bet there's some kind of a diagram showing what happens with surface tension. Let's see what this is. Yeah, so I'm going to open this in a new tab so it's bigger. The title of this webpage up here says surfactant, and I think that may be the name for soap molecules. But so this is a soap molecule. It looks kind of like a sperm. I don't know if you were thinking that, but related to biology, it looks sort of sperm-like. And then you can see the water molecules right here. And the soap has it has a head that has charges on it, positive and negative charges. And then it's got this tail that doesn't have charges. So it's called a polar head and a non-polar tail. Polar just means there's a positive end and a negative end to the head, but the tail doesn't have any positives or negatives. So which one sticks to the water molecules? The water molecules have charges. So which end of the soap would stick to water? I'm going to pick somebody.
Aiden.
Aiden, are you out there? Oh, I don't see Aiden.
RJ.
RJ, what do you think? I'll give you some hints here. Let me show you another. I'll show you the charges on a water molecule. So there are probably some good diagrams and some bad diagrams. Here's a simple one. So there you can see there are positive hydrogens and negative oxygens, and the two water molecules stick together, positive to negative. So if that's what a water molecule looks like up close, is that going to be attracted to this head of the soap that has the charges on it, or is it going to be attracted to the tail with no charges? What do you think, RJ? 50-50.
Head.
The head, right. And that's what's going on here. That's all the soap molecules, they arrange themselves so that their heads are touching the water. So the water, in this dish, all the water molecules on the surface had been holding onto one another really tightly, grabbing on. And when I dump that soap in there, it touches the water molecules and sort of breaks their connection. Now, another cool thing soap does, water doesn't like fats. Fats are non-polar, and water is polar. So water would rather stick to itself than stick to fats. Soap molecules have this tail that can stick to fats and the head that can stick to water. So that's why soap is good for washing oily things off your skin. If you have some oil on your skin and you just rub water on yourself, the water won't pick up that oil and take it away. But if you have water and soap, this polar end of the soap attaches to the water, and the non-polar end of the soap attaches to the fatty stuff or the oil that's on your hand. And that's how soap works. So let me see if I can find a picture of soap molecule attacking oil. Or maybe I should say washing. Ooh, we're going to see a bunch of coronavirus things here. It's related to the coronavirus too, but let me come up with a new search page. So soap molecule surrounding oil. I don't know if this is a great. Well, maybe we'll look at this one. Open a new tab. So here we've got this. This isn't great, but it's water all around, and then there's a drop of oil in the water right there, and then these soap molecules. You can see them. They've arranged themselves with their polar heads sticking out, touching the water, and their non-polar heads sticking in, touching the oil. So that's how soap washes things off. I was kind of curious about this. This is, how does soap work on the coronavirus? I don't know. That's probably more than we want to get into right now. But basically the properties I've been talking about, I think these non-polar tails on the soap molecules, they grab onto the outside of the coronavirus, which is non-polar. It's kind of an oily, fatty membrane. And the polar head, that attaches to the water. So you go wash your hands in the bathroom and scrub, and you're moving the water around, and that's moving these soap molecules around, and then they're ripping the membranes of the coronavirus apart. At least that's how I understand it. All right, time to get back to class number 70. Oh, by the way, if I totally covered this paper clip right here, the one that you see in the picture, if I covered it with soap, it wouldn't float anymore. So I tried putting wax on it last time to make it float better, because I thought it would repel the water and make it float better. It didn't really help. But covering it in soap prevents it. There's no way you can make a paperclip float if you cover it in soap, or if you just put soap in the dish. Review the homework. All right. I may have to print this homework out and do it myself. So let's first go to the... So everybody get your homework out. Sorry, I'm a step behind. You were supposed to do this practice quiz. There's a video of me doing it right there. But I'm... Uh-oh. Oh, I see what's going on. I gave you the whole handout, and all you had to do is the last page. So I actually do have this handout, or this practice quiz. So let me switch to here. I want you looking in my notebook. There we go. Turn that around. It was this one. And if you don't have your, well, I guess you don't really need your colored pencils for what we're doing in class today, but I'm going to go grab a couple of colored pencils. Alright, I've got way more colored pencils than I need here. Stealing them from my 9-year-old. There's green and brown, the blue, and the red. Alright. And then I just need my regular pencil. But all my pencils I'm grabbing for are out of lead. Now I found one with lead, but it seems broken. All right, first step. And by the way, if you can't do this now, you should be getting kind of concerned. You should go back and watch the videos, because with the project you're going to have to do this. I'm going to show you the rules for creating your own continent in just a few minutes. And then it's going to be time for you to start drawing the climate features of your own continent. So first, there's low pressure at the equator. I always start there. And then all the other pressure belts alternate. The center of the next one is at 25 degrees. High pressure. And then the next one's at 60 degrees, from 55 to 65. Low pressure. And there would be another one down here from 20 to 30 degrees south too. The winds go from high pressure to low and clockwise in the north. Hey Renee, will you close that door for me? I don't think my wife heard. And counterclockwise in the south. So the winds look like that down there. The ocean currents near the equator, they always go the same way as the winds, and they're warm. They're warm if they've been at the equator for a while. So this is there's going to be a gyre right here. Go like that. This looks like it'll just go on around. If the continent kept going down, then this would split and follow the coast, but the wind is just going to keep blowing that. This water up here, this is all cold because it's coming from a cold place. Like that. But right here, it's going to go like this. Two ways to understand that. One is there's a gyre here that goes this way. The other is the current hits the coast and splits. Some of it goes around that way, some of it goes this way. Then for the major rainforest, that's always where the low pressure is. It's going to be a little bit bigger on the warm water side. So I'm making it smaller here. Instead of going right up to this edge, I'm just going to there. And that's it for that. The major desert is going to be up here. Ooh, this brown looks like black. Let me find something that looks like real brown. So the desert is where there's high pressure and it doesn't quite touch the ocean. Then the coastal wets, wherever the wind is coming from the water. There. And there. And there. I guess I skipped the rain shadow. You can do this in whatever order you want. The rain shadow is where the wind hits the mountain. So the wind's going to go across. D is going to be wet. And the mountains are wet. N is where the wind hits. So N is wet. And the mountains are kind of wet. And the back sides here, this is the dry side. And this is the dry side. And then last, the humid climates. I would encourage you to find a different color if you have multiple colors, a different color for the humid climates on your project. So this is going to be my symbol for humid climates. I'm just going to use pink today. Humid climates are climates where there really isn't anything else. So it's one of these white spaces and we're near the warm water. So all along through here, this is humid. And I would keep it out of the high pressure there. And around here, this would be humid. And then down here. So now, answering my questions. High pressure belt would be one of these. So A, B, D, I, O, R, and U. What's my pattern here? A, B, D, I, O. Looks like I've chosen letters that kind of go down the left side of this mountain. So I is the one there. Low pressure belt, that would be R. When does wind blow toward the northwest? People have trouble with northwest or just compass directions. Remember the never eat soggy wheat? So northwest is in between north and west. I'm looking for a wind that's doing that. And those are these winds down here. So letter U is the one that would work. Which two letters is there? Or two letters. This should just say which letter. There's only one here. Which letter is there a cold current, A or U? It's at A, not at U. And where's there a cold current? That would be G, not L. Major rainforest is going to be one of these, Q, R, S, or T. So it's R. Major desert is one of these. It's either going to be H, I, or J. So it's I. Coastal wet climate, well, it could be M or C, and the only choice here is C. Wet caused by the rain shadow effect, it's either going to be N or D. D is the only choice. Dry caused by the rain shadow effect is either going to be E or O, so it's O. And then humid would be one of these pink areas that I've done. The only one that's only pink is F right there. M is sort of coastal wet and it would be humid. Where does the ocean current flow directly toward the North Pole? So I'm looking for a current that's going straight up north, right there at letter L. That's the only place it's really doing that. And where does it flow directly toward the east? So it's going to the right on the map. That would be a letter A. All right. I think on my website I wrote down when you'll have a quiz over this, but maybe I didn't. Let me go back and check. So gold people, you're going to have a quiz just like that on Friday. And blue people, you're going to have a quiz like that on Tuesday. Does anybody have any questions about anything that I did on this map? Remember last time when I said, every time I ask, does anybody have any questions? Nobody ever has any questions, but I keep asking anyway. All right. Well, if you ever happen to have a question, please ask. My physics students ask me questions, by the way. All right, let's go back to the plan for the day. So this rising air, sinking air practice quiz. I was originally thinking that we would do that in class. And then I was thinking this would be a good assignment for you to do at home. And then I was thinking maybe we should do it in class again. So I think we should probably just do this together. And I think what I'm going to do is I'm just going to, we'll do this one step at a time, and I'll pick people to answer as we go. So let's all go to Google Classroom. Hopefully you can minimize my window so you can just hear me. And go to Google Classroom and open up class number 70, practice number 1, which may end up being the only practice, but practice number 1 there. And then open up this Google Doc, rising air, sinking air. And that's it. Now, when you get to this, I should see a lot of you popping onto it soon. Who's there? Soli, Anna, let's see, Quinn. All right. So you're all there. You're going to need to go up to the file menu and make yourself a copy. So I'll make myself a copy too. I'll just call mine Stapleton copy of rising air, sinking air. And I'm going to close my original one so I'm not messing it up. I tend to do that. I get on the original documents and I mess them up for people. All right. So this is where I'm going to be choosing people from the audience today. And I should probably write down your names so that I know who's here. And so that I don't keep using my popsicle stick app to call on people who are at home. So I've got Jace, RJ, Anna, Tommy, Soli. Oh, who's that? Harriet. I should know Harriet's clouds by now. Elijah, Quinn, Megan, Reagan, and Cassidy. All right, so we're ready to go. I'm going to keep my, let's see, I wonder if I can keep my picture here and still type into this or do stuff. So I'll go first. This is going to be, I think this will be one of the easiest quizzes ever. You're going to have a quiz over this too. This is the quiz. It'll be exactly like this. You could totally memorize this, but I think that most of you will, I think you will understand it because we've been over it so much. It's a good review. Part 1 is about evaporation, Part 2 is about rising air, and Part 3 is about sinking air. These are super important concepts. So I'll start. The sun shines on the Earth's surface, causing the Earth's surface to heat up. If there's water on the Earth's surface, that water heats up, and so does the air near the ground. This heating causes the speed of water and air molecules too. And to answer this, oh, looks like my picture went away. I'm going to do Control U. That's how I'm going to choose my answer. So that's the right answer, to increase. So if I were to draw a picture of this over here, here's the sun, beating down on the earth. Maybe there's some puddles or lakes or rivers or whatever, and these start to get hot, and the molecules will move faster. Molecules speed up. So these air molecules right next to the ground and the water in the puddle, this is all speeding up. That's kind of what I've got so far in this. All right, so next one. Let's see, Harriet, you're up next. This eventually, the water molecules gain enough energy to, what are they going to do, Harriet? Evaporate or condense? They're heating up. They're speeding up. What's that going to make them do?
Condense?
Condense? No, it would be evaporate. So, I'm going to draw a little picture on here. So, if this is ice and this is liquid water and this is gas, so to turn from a liquid to a gas, that requires heat. To turn from a gas to a liquid, that requires cooling. And I'm just going to write invisible here. That's why I haven't drawn anything over here where the gas is. So if you heat up some liquid, you get gas. And this is also called evaporation. Turning from a liquid into a gas. And then cooling is the opposite. That would be condensation. And then we're not really, this doesn't come into play at all in this little activity, but with ice, if you heat it up, that melts it. And if you cool it down, that freezes it. So evaporation is kind of like melting. Evaporation is going to a higher energy state. So liquids don't have quite as much energy as gases do. So in this case, the sunlight shining on the puddle is liquid, and it's going to turn into a gas right around here. I know you can't really see a gas, but I'm going to draw it as a sort of a bubble of gas there at the surface. Oh, in this process, this is evaporation. So the water is going from visible to invisible as it turns into a gas. All right. And my answer is evaporate. So just reading over what I've got so far. This heating causes the speed of water and air molecules to increase. Eventually the water molecules gain enough energy to evaporate. So they're turning, I'm not going to say that. Their state of matter turns from blank to blank. So let's see. Cassidy, what does their state of matter turn from? If the water's in puddles on the ground, what is it?
Liquid.
Liquid. And what's it about to turn to? Does it turn into a solid or a gas as it heats up?
Solid?
That would be if it freezes. So if you...
Oh, yeah.
Yes, yeah. That's okay. That's all right. This is practice. So... All right. So just going to my picture, I think I've got all this in my picture. We've got the sunlight shines down on the earth, heats things up. It heats up the surface. That heats up the air next to the surface. It also heats up the water that's on the surface. Some of the water evaporates. It turns from a liquid in the puddle to a gas. So now we've got this air near the surface it's got nitrogen and oxygen and other stuff, but it also has H2O in it. That's a gas. So everything so far is really about how the water is turning into that gas. The water molecules leave the ground to become a blank part of the warm air near the ocean surface. All right, Reagan, should this be visible or invisible? After the water molecules have left the ground, are they visible or invisible?
Invisible?
Invisible, yes. And that's because they're a gas. So in my picture, I know I drew a circle here showing them, but that's just so we can visualize them. They would be invisible. This liquid water, you can see Water that's a gas you can't see. Next step. As this air gets warmer, its volume begins to... Okay, so think back to one of our early units. What happens to the volume of a gas as it gets warmer? RJ, what's going to happen to the volume? And do you want me to... I'll remind you what volume is. Volume is size. So does the air, when it gets warmer or hotter, does it expand or does it shrink, RJ?
Expand.
Expands. So that's going to be, the volume will increase. Now density. So if the, let me draw a picture of it on here. So here's the air, and it's expanding, so it's going to grow and get a little bit bigger, and maybe I'll show it expanding even more, getting even bigger. All right, so as that gas has gone from being this big to that big, what's happening to its density? Tommy, what's this next one? As this volume change causes the air's density to increase or decrease?
Decrease.
What's that? Decrease, yeah. Remember, density is crowdedness. So the air here, let me just zoom in on it. If you have some air and let these 4 dots represent the amount of stuff in the air, if the air expands, now the 4 dots are spread out more, so they're less crowded. So the density is decreasing. So as this air sits here and it heats up and heats up and heats up and expands, it's becoming less dense. And this density change, so a decrease in density causes the air to do what, Quinn? Is the air going to rise or is it going to sink if it becomes less dense?
Sink.
It's going to rise. That's okay, though. So dense things sink, less dense things rise. Let me see if I can find a good way to demonstrate. Oh, picture, here's some water, and let's say that I have I've got a balloon behind me. Hold on, I'm going to grab it. So I've got a real balloon to use. It's one of the benefits of working in the toy room here. If I had this balloon and I tied it off, this is going to be kind of a waste of a balloon, but this isn't a very good balloon. I've tried this with other things. And I tied a big rock to this. So here's my balloon that I didn't really inflate. And here's a string, and here's a big rock. The whole thing is going to sink. I mean, the whole thing will go down underwater. Overall, the density of this is too dense to float. So, but if I blew this up, or just if I could heat this up, or I could do something so that the molecules inside this balloon would push out and expand the balloon and make the balloon this big, then they can make the rock float. So I don't know if this is a great example. Maybe a better example would be trying to think of something that if you just leave it alone, it floats, but then if you compress it, I bet. So if I had a ball of aluminum foil, oh, I've got one. Hold on, just a second. Okay, almost back. So here, I have a ball of aluminum foil, or I'm going to soon have a ball of aluminum foil. And it's made out of aluminum. I'm going to put it in the water. Will it sink or float? Floats! Now, what can I do to make it sink? Anyone? Well, I'm guessing that if I squeeze it hard enough and I compress all of these bits of matter into a smaller space, I can make it sink. But I may be wrong. Okay, now. Ah! I need a hammer. So it must have some air still trapped in it. But it's coming a lot closer. Okay. See if I can smash it with a pepper shaker. Yay! I made it sink. All right. So, all that just to show if you... I can't even really remember what I was showing, except I think that if you compress something, it becomes more dense and it sinks. And the opposite would be if I could somehow fluff that back up, it would be less dense and it would rise again. So, to sum up what's happening so far, or what should be happening so far, the sunlight is heating up the Earth's surface. That's making the water in the puddles. The particles are moving faster and faster. They move fast enough, they turn into a gas, they evaporate and go into the air. The air is getting hotter, so it's expanding. Just the opposite of what I did with that aluminum foil. And expanding causes it to become less dense, and when the density decreases, it rises. So, all right, so let me just reread this last paragraph. As this warm air gets hotter, the volume begins to increase, so it grows. This makes it less crowded, so the density decreases. This density change causes the air to rise. All right. And I totally appreciate all of your answers, and the fact that we're getting wrong answers is good, because that means you don't already totally know this, so this isn't a waste of our time. If you knew it all, this would kind of be a waste of our time. So part 2, rising air. As the rising air moves higher into the atmosphere, it encounters blank air pressure. Higher air pressure or lower air pressure? Anna, as the rising air moves into the sky, as this goes up, is it going to encounter higher air pressure or lower air pressure? And I guess, how about if I say stronger or weaker air pressure as it goes higher?
Weaker.
Weaker, yeah. The higher and lower is kind of confusing because because as you get higher, you want to say things are getting higher, but as you get higher, it's weaker. And I don't know if I asked why. Yeah, I think I did. You can do the next one too, Anna. It encounters higher air pressure because there is blank air above it. More air above it or less?
Less.
Less. So that explains it. So the higher you go, the less air there is above you, and the weight of the air above you, that's what's causing the air pressure. This change, this change in air pressure causes the volume of the rising air to, okay, let me draw a little picture of this. It's getting so messy, but that's okay. Here's the air going up, and if I draw the air like this, and I draw the air like this again, here's the air pressure pushing on it when it's here, and then the air pressure up above is less. So the arrows pushing in from the outside decrease as we go up. Jace, what's going to happen to the air? Is that going to make it expand or shrink when the pressure around it decreases? Jace, you there?
Give me a sec.
Sure. So, as the rising air moves to higher into the atmosphere, it encounters higher... Oh! That's not the right answer. It encounters lower air pressure because there is less air above it, and this change in air pressure causes the volume of the air to expand or to shrink. What do you think?
Expand?
Expand, yes. So if there's more air, or pressure around something, that's going to squeeze it in. So, all right, I'm totally switching to a new picture now. Sometimes you see bubbles rising up from the bottom of a fish tank, and artists will draw them like this. But the reason they do that is because they really do expand. When they're deep down, they're compressed by a lot of pressure. But then as they start to rise up, the pressure squeezing them isn't as strong until they get to the top, and then there's very little pressure at the top. So as air rises, it expands because the pressure acting on the air is weaker. Next one. So this expansion or compression, I guess I'll go ahead and fill that one in for you. We know it's expansion of the air causes the temperature of the air to change. I have to flip back over to my sheet here. So as the air expands, its temperature changes. Quinn, what's that going to do to the temperature of the air if you have air that is allowed to expand? You can squeeze air, or you can let it expand. If you let it expand, what happens to the temperature?
Does it get colder?
It gets colder, yes. So compressing things, we've been over this a lot before, compressing things heats them up, but allowing things to expand cools them off. So that's going to decrease the temperature. Now these are simple questions in the sense that they're like multiple choice with only a couple answers, but I don't know if you've noticed it, but we've been over just about everything you've learned so far this year on this one page. All right. Just getting you up to speed on where we are. The air is expanding, and that causes it to cool off. So this cooling, this new change in the temperature of the air, causes the speed of air molecules to do what? Solely.
Decrease?
Yes. So the speed of the air molecules decreases. All right. Oh, I don't know where I'm going on that page. I had to close the door. And next, the change in the molecular motion. So the slowing down of the water molecules causes them to change state again from blank to blank. Let's see. Elijah. So this air, let me go back to my picture and then this air is going up, it's rising, it's expanding, it's cooling. The particles are slowing down. So the water that's in this air is going to change from what state to what state?
From gas to liquid?
Gas to a liquid, yes. So it's been a gas ever since it evaporated. It was a liquid in the puddle. It evaporated on the ground, turned to a gas. As the gas rose and expanded and cooled off, that's going to cause it to turn back to a liquid. So where's my page? Right here. So it's going to turn from a gas to a liquid. And this produces, and I can't believe I left out the word condensation. So this is condensation that's happening here. This produces a cloud, or does it produce clear skies? Harriet, what do we get when this happens? When we turn from gas to a liquid?
Is it clouds?
Clouds, very good. And to summarize, this whole thing's been about rising air. Rising air wet, or is rising air dry? Does anybody want to answer it? If you want to just answer it, just blurt it out. Ms. McGurk, if you had to choose one, rising air wet or rising air dry?
I'd say wet.
Wet, very good. Yes. So this is the reason for that trend on our maps. Everywhere on this map that I have green, this is rising air. There's rising air at the equator because of this big low pressure belt because of all the hot air. There's rising air at these coastal wet areas because to come onto the land, the air has to rise up. There's rising air on this side of the mountains because it's got to rise to go over the mountains. Same thing here, same thing here. All these places, it's wet because of the rising air. So, do you need something? It's got to be fast. Yeah. Sorry. Interruption there. Now, sinking air. This is going to be pretty much the opposite of what we just did. And it should go a little bit faster. I can't remember who I've called on, so I'll just kind of randomly do this. In other places, such as the horse latitudes, air sinks. As the sinking air gets lower, it encounters what kind of air pressure? So we're talking about air coming down from the sky now. Here's the Earth's surface. Here's the air coming down. As it comes down, it encounters what kind of pressure? Megan, what kind of pressure would it encounter on its way down?
I'm not sure.
So, Megan, is there more pressure when you're down low, or is there more pressure when you're up high? Where's there more air above you? When you're down low or when you're up high?
When you're down low.
Yeah, so as this air comes down, like when it's down here, there's a bunch of air above it. When it's up there, there's not much air above it. So as the air sinks, is there going to be more pressure or less pressure acting on it?
Less pressure.
Actually more. So you go down, this would be another way to think about it. This is like going to the bottom of a swimming pool. As you go down deeper and deeper underneath, if this is the top of the atmosphere, the deeper you get, the more air there is still above you. So as air sinks, there's more pressure. Sinking air gets lower, it encounters higher pressure. And I'm going to change that to stronger and weaker because the higher and lower thing is confusing because it's backward. The lower you go, the stronger the pressure is. So low means high pressure, which is confusing. Hopefully I'll remember to fix that. I'm going to make a note on my paper right now. Fix high and low. Because there is... Ooh, Megan, you can do this. As the sinking air gets lower, it encounters higher pressure because there is more or less air above it. What would you say? Megan again.
More.
More. Very good. This change in air pressure causes the volume of the sinking air to. So this change in air pressure is stronger pressure, increasing pressure. What's that going to do to the volume or size of the air? Reagan, what's it going to do to the volume of the air? If you have more pressure, is that going to make the air bigger or smaller?
Smaller.
Smaller, it's going to shrink. And this, so Reagan, I'll ask you this again. Shrinking, would we call that expansion or compression? Which one is the right word there for this, for the air getting shrunk?
Compression.
Compression, very good. All right, so this compression of the air causes the temperature of the air to do what, Tommy? When you compress air, what happens? Does it get hotter or colder? Hotter. So the temperature is going to increase. The new change in temperature of the air causes the speed of the air molecules to do what? Cassidy. So if you increase the temperature, are the air molecules going to move faster or slower?
Slower.
They'll actually speed up. So temperature means if you heat them up, you give them more energy and they move faster. So the temperature is going to increase. And if there are clouds in the air, this change in molecular speed causes water molecules in those clouds to change state or phase from blank to blank. So if there's a cloud, what is the phase of matter of the cloud? Anna, what would a cloud be? Solid, liquid, or gas usually?
Gas.
No, because we can see it. And if we can see it, then it can't be a gas. So guess again.
Liquid.
Liquid. Clouds are made of little tiny liquid droplets. And if those liquid droplets gain energy, what are they going to turn to? Are they going to turn to a solid or a gas?
A solid.
No,
a gas.
A gas, yeah. If you heat them up, they're going to turn into a gas. And this produces, RJ, if the clouds are turning from liquid into gas, is this going to produce a cloud or clear skies?
Clear sky.
Clear skies. And finally, to summarize, sinking air is... Who can put the nail in the coffin here? Solely. Sinking air is wet or sinking air is dry?
Dry?
Dry, very good. All right, so this whole part 3 here is about why sinking air is dry. And this whole part 2 is about why rising air is wet. And this part 1 is sort of about the water cycle. And I don't think we're going to do anything with the project today, so you don't have to worry about that. I've taken enough of your time here, and this has been grueling, plenty grueling. But let me just really briefly summarize this whole thing on a nice sheet of paper to try to make it sound really simple after it's sounded so taken so long and sounded so complicated. So here's the quick story. In some places on the earth, like on the equator, we've got puddles, or we have the ocean, or we have rivers, and the sun shines down on the puddles and the water evaporates, and that causes the water to turn into a gas and to just sit here in the air right above the ground. But the ground gets hot, and that heats up the air, and as the air gets hot, it starts to expand and it becomes less dense. And when it expands and becomes less dense, it starts to rise. And when the air rises, there's less pressure up above, so that makes it expand more. As it goes higher, the higher it goes, the less air there is above it. So this is like going from the bottom of a pool to the top of a pool. If you're being squeezed less and less, the internal pressure of that air is going to make it expand. Now, as the air expands, it's going to cool off. So it gets cooler, and as it rises, it gets even cooler because it's expanding. And finally, it gets cold enough to condense. And there are all these little tiny droplets. You get condensation, or air turning into the water in the air turning from a gas back into a liquid. So it evaporates here from a liquid to a gas, and then when it gets cold enough up there, it condenses back into a liquid. Now, for some reason, this whole thing, if this whole thing worked in reverse, if you could just make this air go down like it does at the horse latitudes, it's going to get smaller and smaller and smaller as it goes, because it's getting compressed by stronger and stronger air pressure as it gets lower. So this is cooling, and this one is heating, and eventually, if there's a cloud here, there will be evaporation, which will make the cloud disappear. So cloud disappears. This would be cloud appears. And this is exactly the same thing that I do when I squeeze the bottle. I squeeze it, that's like making the air sink. More pressure is applied. Clouds disappear. I let go, that's like letting the air rise. So, I'm going to change my website, and I'm going to change what's in Google Classroom. The only assignment is for you to try to do this again. So I would go back to Google Classroom, make a new copy, see if you can do this on your own. You're going to have a quiz exactly like this, and it'll be when you're in class. I don't know exactly what the next few days are going to hold for us, but it'll be this piece of paper. The only difference is that I'm going to try to get rid of the higher and lower pressures with stronger and weaker pressures. Any questions? Ha ha. Maybe you really have one this time. Okay, I'm going to take one last look at the website just to make sure I'm not leaving anything out.
I have a question.
Ooh, a question. Yes, Anna, please ask.
So we're taking that paper test on Friday, but when are we taking the test where we like draw the things out?
That'll be done on. That's just going to be done in class or during class time for the next few days. You're going to be drawing. It's a more of a project than a test, or I guess you could think of it as kind of a take-home test. You'll do it little by little, and that's really all we're going to be doing tomorrow and Wednesday and Thursday. So we'll have plenty of time. I'll give you some pretty clear instructions on that. If you want to, if you see what's on my screen right now, if you want to click on Climate Map Project PDF version and read some of it, it's kind of an overwhelming amount of information to just read, but it really describes everything clearly, how I'm going to grade it, what you have to do. But I'll go through it thoroughly tomorrow. It's basically just you're going to draw your own map and one thing at a time explain the climate features. But I can help you.
Okay. Thank you.
Yeah, you're welcome. So really, the only on demand kind of on the spot quizzes you're going to have, there's going to be one that's like this. Oops. Yeah, one that's like this, where you have to draw these things, and then there'll be some multiple choices. And then there's going to be another one that's exactly like the Google Doc that we just filled out, and you just have to circle the right word. All right? So have a good day. Just do this, make another copy of this, or undo everything you did and then do it one more time. That's it. Bye.